Welcome. My name is Eren Baydemir, and I'm a principal product manager at the Amazon Redshift team. I'm here today with my colleague Harshita Patel, principal specialist solution architect at AWS, to talk about some exciting features that we have recently launched and show them in action to help you get started with. And in the next few minutes, I will briefly introduce those features, discuss how they can help you with the analytics workloads, and then Harshita will be demonstrating how you can start with these features and use them together with Redshift's existing integrations and capabilities. Query Editor V2 is an easy-to-use web-based SQL client for Redshift that improves the data analyst productivity. It allows you to browse database objects, load data into your tables, easily write and run SQL statements, visualize query results, and most importantly, collaborate on your data analysis using saved queries and SQL notebooks. Query Editor V2 provides two new capabilities. You can now import data files directly from your computer into your tables, which eliminates the need for manually uploading your files into Amazon S3 and run copy statements manually for quick ad hoc data analytics queries. We also recently announced the schema detection capability that automatically analyzes and extracts the column types from your data files, which you can leverage to create tables automatically for your data loading operations on Query Editor V2. Another recent announcement that we have made is the general availability of the support for merge command in Redshift. Using the merge command, you can apply source data changes to Redshift tables with a single SQL command instead of executing a series of data manipulation statements. When using multiple statements to update or insert rows based on your existing data, you can use the merge command to eliminate the risk of inconsistencies between the steps you take by ensuring that all operations are performed together in a single transaction. And this is especially useful for customers who are migrating from other data warehouse systems or who regularly need to ingest frequently changing data into their tables. Simply put, merge command provides an easier way to conditionally insert, update, or delete rows in target tables based on the existing and the new source data. In February, we have announced another set of SQL enhancements in Redshift to help some use cases that requires advanced aggregation capabilities. By using the rollup, cube, and grouping sets, you can simplify your multidimensional analysis without building complex processes and running multiple statements to aggregate and analyze core business facts against multiple dimensions, such as product category, geography, date, and etc. Customers requires the best-in-class security and compliance for their data analytics. And a big benefit about using Redshift is our built-in security and compliance, which is a part of the Redshift experience out of the box. This spans across authentication, access control, auditing, encryption, and compliance for regulated industries. For authentication, Redshift provides built-in integrations with AWS IAM and uses IAM Identity Federation to support popular third-party services such as Azure Active Directory, Okta, and Ping Federate. For managing access to your data, you can use fine-grained and role-based access controls, both for your Redshift data and for your data lake. Auditing, connection, and user activity events are simply handled with the built-in integration with AWS CloudTrail. Your data is encrypted in motion and at rest. And finally, Redshift integrates with AWS compliance programs to help customers to understand the robust controls in place at AWS to maintain security and compliance in the cloud. So with the role-based access controls, you can apply fine-grained security at the column and row level on your tables. In addition to the wide variety of features and capabilities to help you to control access to your data, we have recently announced the general availability of two new capabilities: dynamic data masking and lake formation managed data shares on Redshift. Customers want to protect sensitive data based on the job roles and permission rights of their users, or the levels of data sensitivity by masking their data when needed. They want to customize how they mask data with the fine-grained policies. And with dynamic data masking, which we recently launched, Amazon Redshift can apply data masking policies dynamically, where customers can easily protect their sensitive data without making changes on the actual data. Masking can easily be configured through a SQL interface and provides a simple approach to mask data fully or partially based on the requirements. So Amazon Redshift enables flexible data mesh architectures where you can seamlessly share data within or across clusters, accounts, or organizations in live format without losing transactional consistency. Sharing data also helps you to enable workload isolation and also chargeback capabilities. Sharing data between serverless and provisioned clusters within the same or different regions, or leveraging the integration with AWS Data Exchange to subscribe third-party datasets like FactSet further enhances the value that data sharing provides. And now, with the recently announced lake formation fine-grained access control enhancements, you can centrally manage access to your Redshift data shares as well as your data lake resources. With all innovations that we continuously introduce, Redshift enables analytics on all your data and for all your users. You can access data on your local Redshift resources or data on Amazon S3, implement various ingestion and integration options to grow your data, empower machine learning or data processing applications with integrations to Amazon EMR, Amazon Glue, and Amazon SageMaker, and finally provide access to your data for all your users with the tools of their choice through our drivers, data API, or by using the Query Editor V2 for a simple and easy to use data access. We can't wait to see how these features will help you with your analytics workloads and the innovations that you will cultivate. I will now hand it over to my colleague, Harshita, for a demo to see these exciting features in action.
Thank you, Aaron, and thank you all for joining us today. Let's dive into the demo. For this demo, we'll use a use case of a company which is based in the FinServ. They are providing credit card services to their customers, which are situated globally. This application is business critical analytics application. Because of the business critical needs, they require highest level of availability and resiliency. They also want to become more data driven. So they want to modernize their data architecture on AWS using Amazon Redshift. Example Corp has also shared their business objectives and functional objectives. From a business objective, primarily on the security front, they want to protect their sensitive, personally identifiable data by using masking. They want to provide access for the users who have access to sensitive data. They should be able to see the data in clear text. For users and roles who should not get access to this sensitive PII data, they should be able to see masked values. They want to open the doors for the data analysts to do trend analytics over their historical as well as current data, and also provide the ability to join their transactional data with which is coming from their operational databases to this historical and current data. The key ask from them is to simplify building machine learning operations or pipeline using simple SQL skills. And the key goal they have is to use that machine learning for prediction to identify if the payment transactions are fraudulent or not. Once they get insight if the transactions are fraudulent, they want to provide that notification and insight to the finance team to take appropriate actions. So the need is to securely share this data to the finance team without data duplication. From the functional perspective, their objectives, as this is a business critical application, their ask is to have high availability with recovery point objective of 0 and recovery time objective of less than 5 minutes. They also want to simplify their data processing. They currently have batch, mini batches, data trickling in, but they also want to take it a step forward with the need to ingest that payment transactions in near real time. So based on this business and functional objective, let's work backwards from these objectives that the customer has shared. As part of the demo, we'll use the Amazon Redshift newly announced as well as existing features to see how we can enable each of the customer's requirement. To meet the high availability and resiliency requirement, we will use Amazon Redshift multi-AZ feature. You, as a cloud admin or a cloud engineer, when you create an Amazon Redshift provision data warehouse with multi-AZ feature, it deploys compute in 2 availability zones, serving through a single endpoint. So if one availability zone goes down, the workload is still served by the compute in the second availability zone. Let's see how we can get started with creating Amazon Redshift provision data warehouse with multi-AZ feature. For this, I'm going to pivot to AWS console. We'll start with the Amazon Redshift landing page. We'll then click on Create Clusters, create Preview Cluster. We'll give this Data Analytics as the name of the cluster identifier, choose the preview track 2022, and select multi-AZ deployment as yes. We'll click on Load Sample Data, which is tickets data as part of cluster creation, and enter a password. We'll select the default IAM role. You can choose the default, or you can also choose your own network VPC as well as security group. For the purposes of the demo, I have pre-created the cluster data analytics. As part of creation, the tickets data is already loaded. To start analyzing, we'll use the thin client query editor v2. Through query editor, you can connect to your serverless endpoints as well as your Amazon Redshift provision clusters. You can navigate through the databases, schema, tables, views, and you can also look at the definition. So this tickets data was loaded as part of the creation, and it also comes with a pre-built notebook with queries. So let's go ahead and get started with our analysis. So we'll run this. This is going to run all the tickets data related analytical queries. So now let's review. As these queries were executing, we'll shift to cluster and click on query monitoring. This is the query monitoring dashboard of the queries which are running, completed queries. And we will see that compute type over here is primary. So this will provide you the operational metadata and the operational information of whether the queries were served through primary or the secondary compute. So with Amazon Redshift multi-AZ feature, this enables you to provide high availability and resiliency for your business critical workload. The second objective is to simplify, but also make incremental data processing scalable. For this, we will use the merge function, which is recently GA'd. So for incremental data processing, when the incremental data comes, you have the need to compare it to the data which you already have in your data warehouse. Based on the condition, you need to take appropriate action based on your business rules, whether you want to insert, whether you want to update existing fields, or you want to delete existing records. So for this particular demo, we will use customer information incremental data, which is sitting on Amazon Simple Storage Service, Amazon S3. The target table, which is customer information target, is loaded into Amazon Redshift local table. So let's see the simplification of merge function for your incremental data processing. So we'll start off by creating customer info stage. This is going to serve as to load our incremental data, which is on Amazon S3. So we are going to load this table with the data on S3. And as soon as this, using the copy command, as soon as this is loaded, we'll run this query to see what are the existing customer IDs coming through the data and which are the newly arriving customer IDs in the incremental data. We'll also review the target table, which is on Amazon Redshift Local, which is already loaded with customer records. In order to do incremental processing, this is customer information stage as the source and the target is info target. Based on the matching conditions of customer ID and full name, we'll update email address and phone number. And when there are no matches, which is newly arriving records, we are going to perform insert operation. We'll go ahead and run merge function. And now let's review our target. So with this target table, we are only filtering on the incoming customer IDs. Records 6205 all the way to 6207, they are newly arriving records which we inserted, and the existing customer ID records, the phone number, as well as the email address got updated. Let's expand the email address column. So with merge, provides you the ability to do incremental data processing based on the conditions that you have for your business rules to insert, update, delete in one transaction. Now, in order to meet the business objective of protecting sensitive data by masking personally identifiable fields and only providing access to the users who have granted the permission versus masking it from the roles or the user who does not have access. So in this example, we are going to use customer information, the same table that we did incremental processing, and there are two PII columns on it, phone number, email address. For this feature, we will use Amazon Redshift dynamic data masking, which is based on role-based access control for fine-grained security. Security admin is a persona who creates the masking policy, attaches the masking policy to tables for specific columns, and then also attaches those masking policy to specific roles. So in this example, we'll attach a masking policy to completely mask email address and redact phone number. These masking policies can be customized. So we are going to use example of Miguel, who is a data analyst. When Miguel queries customer information, Miguel should only be able to see masked phone number and email address. Let's dive into the demo. So first we'll get started with a role-based access control setup. We are going to create the user Miguel, as well as a role, data analyst role, and we are going to grant this data analyst role to Miguel. Followed by, as a security admin, we'll create a fully masked policy for email address and a redacted policy for phone number. You can absolutely customize your policy based on your needs. Once these policies have been created, we will then go ahead and attach these policies to customer info target. So mask full policy is attached to customer info for email address and redacted is attached for phone number. And we have granted or attached that policy to data analyst role. Let's go ahead and run this. Now, finally, let's run a query as Miguel. So we are setting the session authorization to Miguel, and we will query customer info target. So as Miguel is only able to see the email address and phone number, which are masked. So email address is fully masked and phone number is redacted. So with dynamic data masking, which is based on role-based access control, allows you to do row-level security. Role-based access control specifically allows you to do row-level security, column-level security, as well as dynamic data masking. One of the key requirements is to provide a unified view to the end users to do trend analysis. This unified view comprises of historical data, hot data, as well as operational data. This particular feature of Amazon Redshift is federated query. In this example, we'll take a look at, as an end user, we want to identify which states have highest fraudulent transaction, but also dive a little bit deeper into by joining to the operational data, which provides you that live data to identify what are the trends causing those transactions to be fraudulent. As an end user, as a data analyst, or as an end user, you're still connecting to Amazon Redshift. Both of these analytical queries are submitted to Amazon Redshift. When the portion of the data for history needs to come from Amazon Simple Storage Service, Amazon Redshift Spectrum feature comes into picture. And when the data needs to come from Aurora MySQL, that's where the federated query comes into picture. But from the end user perspective, they are still connected to Amazon Redshift. Amazon Redshift parses that query and pushes down the computation to respective data sources, joins the data, and renders the results to the end user. The end user does not need to know where this data is coming from. Amazon Redshift federated query enables this use case. So for data sources, the history data, we are going to use customer credit card transaction history. For the operational data, we are going to use account profile. Account profile is the latest and the live information of a customer's credit card profile or customer profile. And we will load the hot data into an Amazon Redshift local table. Let's go through the demo. The first data source is Aurora MySQL, on which we have this account profile data, which has the information about customer, billing address, as well as FICO score and last contact reason. In the grid below, we are able to see the data directly querying MySQL database. The second data set is the historical data sitting on S3, which is cataloged using AWS Glue catalog. The database is Spectrum Historical. This data is in a Parquet format. AWS Glue provides metadata about the data and corresponding columns and data type. So let's create a unified access to do trend analytics for the end user. Let's integrate Amazon Redshift to Amazon S3 using AWS Glue Catalog. Through Query Editor, we'll create schema. And this schema is going to be an external schema because we are integrating Amazon Redshift with AWS Glue. You can create external schema using Glue Catalog as well as Aurora or RDS Postgres MySQL. Let's select Spectrum Historical as the Glue database and choose an IAM role and click on Create. As soon as you have created this external schema, you can use Query Editor to browse through that external schema as well as review the list of the tables which are cataloged in Glue. Once we have this external schema, let's go ahead and run this query on Amazon Redshift. This feature is leveraging Amazon Redshift Spectrum, but the end user is directly running this query connecting to Amazon Redshift. Secondly, in order to query the operational data on Aurora MySQL, we'll go ahead and create an external schema. We could use the UI, but here we will use the SQL function, create external schema. And now let's review the sample records directly from Redshift. The data is coming from Aurora MySQL. So we are able to see the FICO score as well as the last contact reason. Now let's load the most current data or hot data into Amazon Redshift local table. This table is customer payment transaction current. We are going to use copy command to ingest this data into an Amazon Redshift customer payment transaction current table. Let's go ahead and run this. So we got the data, direct access to historical, as well as the operational data store, and now we have data loaded into Amazon Redshift. We'll now create a combined view, which is going to combine the historical data with the hot data or current payment transaction current on Redshift using view with no schema binding. As soon as we have this view, the end user, as a data analyst, can start writing the analytical query to identify the states with fraudulent transaction. Amazon Redshift now supports grouping set, rollup, and cube. So as we can see, it has broken down by text, fraudulent transactions, as well as it has given a total of payment at the state level. Let's run ahead the query to identify the states with highest fraudulent transaction. We can see New York is the state with highest fraudulent transaction, but there is also an interest to visualize this data on Query Editor. Now that's great. We got insight onto New York being the highest fraudulent state with fraudulent transaction. Let's see what trends from the operational data, which is account profile, causing this. We can clearly see that the payment state versus the customer billing state are entirely different, as well as the last reason the customer contacted Example Corp was either they were traveling or the credit card was stolen. So with Amazon Redshift, federated feature allows you to join your data, which is in your Amazon Redshift local, combine that with your historical data or your data which is on Amazon Simple Storage Service serving as your data lake with the data which is in your operational data store to get live insight. We have the historical data. Now let's consider this use case where the customer wants to simplify their ML ops pipeline using simple SQL. The outcome of this is to run prediction within Amazon Redshift. For this particular use case, we will use Amazon Redshift ML feature. Amazon Redshift ML integrates with SageMaker Autopilot. As an end user, be it a data analyst, data engineer, or a data scientist, when they create this model, they are using SQL. They run create model statement, and the entire pipeline to unload the data from Redshift onto Amazon S3, invoking SageMaker Autopilot, SageMaker Autopilot figuring out the best model for the problem type. Once that model has been created, compiling that model and then deploying it onto Amazon Redshift as a user-defined function. So this entire pipeline has been simplified. From an end user perspective, you are running create model, and that entire pipeline has been simplified with Amazon Redshift ML features integration with Amazon SageMaker. So let's consider a use case. For this, we are going to use customer credit card transaction historical data to train the model. And the model training occurs in SageMaker Autopilot. When the model is completed, it gets deployed as a user-defined function on Amazon Redshift. And as an end user, when you are using that user-defined function in your SQL queries in Redshift, the inference and prediction is occurring on Amazon Redshift. Let's look at the demo. So first is as an end user, you are creating create model statement, providing the features from the customer payment transaction table. The target is this transaction fraudulent or not, and providing the function fn customer ccft. Let's see if this model is ready. The model state is ready, so we are ready to use this user-defined function on Redshift. The target is this transaction fraudulent? SageMaker Autopilot determined this problem type as binary classification, and on Redshift, the user-defined function fn customer ccft is deployed. Let's check the accuracy of the model by doing prediction and comparing that value with the actuals. Let's run this query, and we are able to see 0.912 as the model accuracy. So with SageMaker Autopilot integration, it allows you to use simple SQL to create the model as well as deploy the model on Amazon Redshift for prediction. If you already have your own model, you can bring your own model into Redshift, and Redshift also supports k-mean clustering unsupervised learning model. Now we have this prediction function. So the key requirement is to ingest the data in near real time, the credit card payment transactions in near real time, and predict if those near real time transactions are fraudulent or not. For this use case, we will use Amazon Redshift, streaming ingestion feature, and the user-defined function for ML, which we created in the previous demo. The data source over here is going to be Amazon Kinesis data streams, which will be generating near real-time credit card payment transactions. In order to integrate with Amazon Kinesis data streams, we are going to create a materialized view in Redshift on Amazon Redshift. Materialized view is going to pull the transactions from Kinesis data stream and physicalizing on Amazon Redshift. The goal over here for this particular objective is to do prediction of fraudulent transactions in near real time. For this, our data source is Amazon Kinesis data streams, where we have the stream created customer payment transactions. In order to generate the transactions data, we will use AWS Lambda. An AWS Lambda function is creating these transactions coming in as JSON format. Let's go ahead and click on test. This is feeding these transactions to Kinesis data stream. Going to the query editor, in order to create this continuous ingestion pipeline and do prediction, first we'll create an external schema from Kinesis. Once this external schema is created, let's review SVB external tables, where we will see the list of Kinesis data streams, and we are able to see cust payment transaction stream. Followed by that, we'll create a materialized view with auto refresh on Amazon Redshift. This is where the transactions are pulled with auto refresh and physicalized on Redshift. The payload type is JSON. Redshift supports super data type, where you can ingest semi-structured JSON, and you can also run analytical queries on top of it. The source is the stream. For the purposes of the demo, I'm going to manually refresh this materialized view. And as soon as this materialized view is refreshed, we'll review the incoming transactions. So let's take a look at some sample transactions which are incoming. And we can see the payload has the details on transaction ID, customer ID, the date, and the time. The goal for our demo is to run prediction. So before we run and call a user-defined function, we are going to transform this data, which is the near real-time data coming in as a materialized view, physicalized in materialized view. So we are going to make this transform data ready for feature engineering. So in this view, we are invoking user-defined function. And now, finally, we want to review from the incoming transactions, which transactions are fraudulent. So there is one transaction which is identified as fraudulent. Let's check the transaction prediction value, which is 1. So the user-defined function did the prediction for this transaction, and the prediction is 1, meaning it's a fraudulent transaction. Now we have this data, the customer credit card payment transaction data, as well as insight into these transactions being fraudulent. Let's share this data with the finance team. So this is where we would securely share this data to the finance team without data duplication. For this, we will use Amazon Redshift data sharing feature. We'll create a data share from data analytics, which we have been using throughout the demo to load data, analyze the data, as well as create ingesting near real-time data and identifying whether the transactions are fraudulent or not, and share it securely with finance. When finance is going to run queries on this data share, it's going to use the compute resources of finance, and we are using Amazon Redshift serverless endpoint for the finance team. So the compute resources are consumed from the finance serverless endpoint, but it's directly accessing the Redshift managed storage of data analytics, providing them live transactional consistent view of the data. As Aaron described, data sharing is a great use case or a feature to enable workload isolation, collaboration, clear-cut chargeback. You can do data sharing within AWS account, across AWS accounts, across AWS region. In this example, data analytics is a provision cluster and finance is a serverless endpoint. Let's go through the setup of data sharing and see data sharing in action. So from the data analytics connection, we'll create a data share, transaction data share. And to this data share, what we are adding is metadata. We'll add all the tables which are in the public schema. Let's go ahead and run that. And then we are going to grant usage on this data share to finance serverless endpoint, which is the namespace. Now let's review what is part of transaction data share. So from data analytics, it's an outbound share type. And this includes the list of tables, views, materialized views, which are part of the public schema. This also includes customer payment transaction as well as transaction stream. From the consumer side, we'll connect to serverless finance. And let's see the data share. So for finance, this is going to be inbound share type. We'll create the database from this data share. And as soon as we have the database created for this data share, you can use Query Editor to browse through that data share, as well as to view the tables, views, materialized views, which are part of that data share. So this is all metadata sharing. Now, as soon as this metadata is visible, or the tables and objects are visible, as a finance user will run the analytical query to identify highest fraudulent states with highest fraudulent transaction, as well as query the incoming streaming data, which is the payload over here, as we see in this example. So with data sharing, it provides you the capability to securely share your data from producers to consumers. You can also do cross collaboration. So to summarize, we started with business and functional objectives. In order to address the high availability and resilience requirement, we created Amazon Redshift Provision Cluster with multi-AZ feature. In order to address the simplification and scalability of data processing using the merge function. In order to do and protect sensitive data, PII columns, by using masking, we use dynamic data masking, which is based on role-based access control. To address the use case of providing a unified view to the end users, Amazon Redshifts integration with Amazon S3 using Amazon Redshift Spectrum, as well as the federated query integration to Aurora, RDS, MySQL, Postgres provides that unified view to the end users to run the analytical queries irrespective of where the data is coming from. To handle the use case for near real-time credit card payment transaction, Amazon Redshifts integration with Amazon Kinesis data stream. This real-time streaming ingestion feature also integrates with Amazon managed streaming for Kafka. To build prediction, integration with Amazon SageMaker, and then securely sharing this data to the finance department using data sharing feature. And the inbuilt capability of rich functionality, which enable this customer to do trend analytics, also use roll-up grouping sets within their query. Amazon Redshift provides JDBC as well as ODBC drivers and data API. You can bring in your tools or products of your choice, be it Informatica, be it DBT, or if you're using Tableau, MicroStrategy, Spotfire, Qlik for visualization. This allows you to integrate your tool set with Amazon Redshift to provide and serve your analytical use cases. I'll now like to hand over to Aaron.
Thanks, Arshida. I hope you enjoyed these features and our demo. And if you have any questions, please reach out to your account team, solution architecture team, or the professional services team. We'll be happy to help. And please also visit the Amazon Redshift new feature page to learn about our new features. Thanks for joining.